Okay. Hi. Sorry for the delay there. Okay. Hopefully this. Okay. Oh, I see that there's something in the chat. Oh, yes. Good afternoon. Okay. Okay. So today I want to do like a couple examples to do with group actions. And and kind of and hopefully prepare so that we can start looking at the C-lob theorems this week. Okay, we just need to know a few things. Okay. Okay, so on Friday I posted an assignment. Right. Okay. On Friday I posted an assignment and it's due this Friday. And so I wanted to do like a question. I wanted to do a question like question 4, except so question 4 on the assignment says to compute the center of some group, and instead I'm just going to compute the commutator subgroup of this group. So let me tell you what's going on. This will just be like an example. So H is this group of upper triangular matrices. And on the assignment, I asked you to compute the center of H. And I want, in this example, let's just compute H prime. In other words, the commutator subgroup. Okay. So to start with, we have to take two matrices and compute their commutator. Okay, and see if we notice a pattern. So let G is going to be an element of H, and H is going to be another element of H. Okay, and we have to compute the commutator of G and H. Let me just do that by hand. Okay. So we have to ask ourselves, we have to find G inverse. Well, we can do that either by guessing or we can just do it by hand. Just to get a formula. And if we row reduce, we'll be able to see what the inverse is. So we do this minus A times this. Okay, and then this minus C times this minus B times this. Oh, sorry. And then when we do this minus A times this, we get B minus CA. Yes. Okay. So this minus B times minus CA. Okay. And as long as I didn't make any mistakes, this should be our inverse. Well, we should just check it because probably maybe I did make some mistakes, you know. So if I check it 1, 0, 0 times this matrix, you need 1, 0, 0. Negative A, 1, 0 times this matrix, you need 0, 1, 0. And this matrix times this last column times this matrix gives me B minus CA minus CA. Oh, so I got a sign messed up somewhere. Oh, it should be CA minus B. Yes, and that will be fine, I think. Okay. So it's a good thing I checked, I guess. Right, so this will tell us the formula for the inverse, and now we can compute. You can compute commutator of GH. It's just GH, G inverse, H inverse, and this is just a product of four matrices. And here's H. And now G inverse. And then the last matrix is just H inverse. So we do DF minus E. Okay. And now we have to multiply all these together. And this will tell us what like some element of the commutator subgroup will be. So like these elements all generate the commutator subgroup. So hopefully these might like have some special form or something. Well, we can hope for the best. So when we multiply two elements, what happens? So we get 1, 0, 0. We get D plus A. We get 1 and 0. We get E plus FA plus B. And then we get F plus C. Then we get 1. And then when we multiply these two together, what happens? Well, it's kind of like the same thing, but okay, so we get 1, 0, 0. And we have minus D minus A. Then we have 1, 0. And then we have this times this. So we have DF minus E. And then plus FA. And then plus CA minus B there. And then we have this times the second row gives me minus F minus C. Then we have 1. And now we have to multiply these together. And we have kind of run out of room. That's okay. Okay, so, but we can see kind of that. We'll try and do it as small as as clearly as we can. Of course, whenever we multiply any two matrices like this is always the first column. And the second column is second column times the first matrix. So in our first entry, we have minus E minus A times 1 plus D plus A times 1. So we have D plus A minus D minus A, we have 0. The other two entries are 0 and 1. And then in the third row, in the top corner, we have like some big mess. I'll just put it as a blank for now. But in the other two entries, we have like in this entry, we have minus F minus C plus F plus C. So we have 0 again, and then we have a 1. And then, so really we just need to fill in this this blank. Well, it's just some big, you know, complicated expression, I guess. It's like df minus E plus FA plus CA minus B times 1 plus D plus A times minus F minus C, and then plus E plus FA plus B. And let's see, there's like a bunch of cancellation you can do. You know, so if you expand this out, you get minus DF, minus AF, minus, oh, sorry, minus CD, minus AC. And now if you try, you can like slowly start to cancel. So you get B minus B. You have FA minus AF. You have CA and minus CA. What else do you have to cancel? You have a DF and a minus DF. And then you still have plus E and minus E. And what you're left with is AF minus CD. That is the only things that are left. Okay, and everything else cancels, which is interesting. Okay, and that's what goes in here. So a typical commutator has the top right entry is just some real number, and these other two entries are 0. Okay, so that maybe tells us that if things like this were a subgroup, then the commutator subgroup would be all the subgroup of all the things where this top right entry can be any real number. Okay, so that is our guess. So from this, we claim that H prime, the commutator subgroup, is those matrices that look like this. is any real number. Okay. And to show our claim, we just need to show that if I take two matrices like this and multiply them together, I get another matrix like this. But this is just a direct calculation. So I get 1, 0, 0, 0, 1, 0, and then I get B plus A, 0, 1. Okay. So what this tells me is that the commutator of any two matrices lies in this subgroup. And any element in this subgroup is a commutator. Okay. So if I call this group, so this is our claim that H prime is this group. So let's give this group a different name. Let's call it like K. Let's define it to be K. So we've shown that the commutator of G and H is always in K for any G and H. In H. Also, you can see that K is a subgroup of H. Okay, and since K is a subgroup of H and any commutator is in K, that means that the commutator subgroup is contained in K. But now we can show like any element of K is actually a commutator. And for that, I just need to check my formula. If I look at 1, A, 0, 0, 1, 0, 0, 0, 1, commutator of that with this matrix. So if I take the commutator of these two matrices and I apply my formula says that this should be the matrix. Well, the top right thing should be this times this minus this times this, right? So that would be 8 times 1. So it should be like this. Okay, so this tells me that any element of K is a commutator, and the commutator K is the set of all the commutators. So therefore, K is equal to H prime. Okay. So we have computed the commutator of H. Okay. Okay. So, this question is just to do some computations. Okay. For now, I want to also talk about remind you of the class equation for a group action. Let me just remind you. Okay. So let G act on a set X. Remember the center of the group action, I'll just write it down. This is the center Z. Okay, the center is all the X's such that gx equals x for all g. Okay. Another way to say this is if gx equals g for, or sorry, if gx equals x for all g, that means that the orbit of this x has just one element itself. Okay. And then let A be a set of representatives of the non-trivial orbits of G, or sorry, of X under G. Okay, so what do I mean by that? Well, just go to the next page to remind you. But basically, we collected all the orbits of size 1 here in Z, and for every other orbit, just pick an element from it. Okay. Okay. So let me explain the definition. So my explanation is that for each orbit O, choose an element of O, say A in O, and oh yeah, for each orbit O of size bigger than 1, and put A in my set of representatives here, and then I just need to know O has to be bigger than 1. Like the number of elements of O has to be bigger than 1. Okay. And what the class equation says is that, so we have this theorem, the number of elements of X equals the number of elements of Z plus summation. So we go over all the representatives of the non-trivial orbits, and we take the index of the stabilizer in G. We sum. Okay, and there's just like a hidden condition would be like, this only makes sense if X is finite. Okay, so I'll just put that as long as number of elements of X is finite. Okay, so that's our class equation. And so in the special case where the group acts on itself by conjugation, this gives us a special example of the class equation, which I want to mention. Okay, so example. Remember this example. So we have, let X just be the same as G, and let G act on X. So remember, X and G are the same thing, but G is going to act on itself like a group, as a group action. And how does it act? By the rule that alpha G X is just GX G inverse. Okay. This is a group action because when you do GHX H inverse, when you conjugate first by H and then by G, that's just like conjugating by GH. And when you conjugate by E, well, E inverse is just E, so it's really just X back, right? So if you compute these two things, that tells you that this formula gives you a group action. And right, so now we have a group action acting on, and now if G is finite, we can use it, we get the class equation. And what are the different terms in the class equation? Well, we can find out. We get the class equation for groups. We just have to figure out, to understand the class equation, we just have to figure out what are the orbits of this group action, what are the stabilizers, what is the center of this group action. And in terms of the center, is just like the center of the group. So hopefully that's good. Okay. Okay, so we have to figure out what all the terms in this are. So first of all, X is just the size of G. And what about Z? Well, Z is all the elements of G, or else, sorry, I'll put it like all the elements X of G, such that GX G inverse equals X for all G. Okay. But if I just rewrite this slightly, it just says that GX, if I multiply on the right by G, it just says GX equals XG. So it's all the X's subject to the relation that GX equals XG for all G. And this is really what the center of the group is. So that's lucky because I have this definition of the center, and it just happens to use the same name as the center of this group action. So that's good. Or else if I would have needed a different name for it or something, if not. Okay. So the center is just the center of the group. What's the stabilizer of X? Well, that's all the G's, such that G stabilizes X, and the action of G is like GX G inverse. Okay. And again, this is the set of all elements of G which commute with X. So this is actually called the centralizer of X. Wait a minute, maybe I should put like the centralizer. No, I'll just leave it like that. Okay. So, and then what's the orbit at X, V, and G? What is the orbit, right? So if we look at GX G inverse, this is the orbit of X under the action of G. This is called the conjugacy class of X. Okay. And this tells us that the number of elements which are conjugate to X, that's equal to the index of this subgroup in G. Okay. And now we might want to like look at, so I want to look at an example of this equation for, maybe a group or two. So let's look at an example of the class equation. This gives us a lot of information about the group we're looking at. Examples. Well, if G is abelian, then the center of G, right? So abelian, remember, it just means that like GH equals HG for all G and H. So if G is abelian, then this means that the center of G is all of G. So the class equation just says that the number of elements of G is the number of elements of the center of G plus 0, if you even want to write that, right? It just says that G breaks up into a bunch of different conjugacy classes of size 1. Okay, so that's not very interesting. So let's do at least one example. Like, what about what are the conjugacy classes, right? So what is the class equation for like one of the finite groups, maybe like D4, right? So we'd have to compute the center of D4. Right. This turns out, so remember what D4 is. D4 is generated by A and B, subject to A to the 4th equals B squared equals the identity, and BA equals A cubed B. Okay. And so an element of D4 is in the center as long as it commutes with both A and B. And you can show that the only thing that commutes with both A and B is just A squared and the identity. Okay, so that's the center of D4. Also, if you rearrange this, it says that BA, B inverse equals A cubed. So that means you have another possible, so that means A and A cubed are in the same conjugacy class. These are in the same conjugacy class. Right? You can also rearrange this to show that, like, let's see, you can rewrite this as you can write this as you can go A inverse BA equals A squared B. That tells you that B and A squared B are in the same conjugacy class. Okay. And then there's only 2 left, and the only 2 left are just what I have A cubed, A squared, B, A squared B. I have A, B, and A cubed B. So what is A cubed B? That is BA, which is another way of writing that's another way of writing BA, B, B inverse. In other words, B, AB, B inverse. It's telling you that A cubed B and AB are in the same conjugacy class. Okay. So I have three different conjugacy classes, and the center has size 2. It is possible we have to, in order to complete this question, we have to show that these three conjugacy classes are disjoint. Like we have to show, for example, that A and B are not in the same conjugacy class, right? But one way we can do that is we can compute the size of the centralizer of elements of these orbits. Okay, so let's take just basically a 2-minute break. When we come back, we'll do that last part, and that's it. Okay, so yeah, let's stop and then just come back for a very short period of time to finish off this example, and that's it. Okay.